Okay. So we've been talking about conditional expectation, right? And I want to do one more example of conditional expectation, if I can. Okay. So one more example of conditional expectation. Then the main topic for today is inequalities. That is statistics inequalities. Okay. All right. So here's one more conditional expectation problem. All right, so suppose you have a store and different customers show up at your store and spend different amounts of money. It's just, this kind of doesn't have to be about a store and customers, or just to have a concrete example, I'll say it that way. That's clearly a very, very general type of setting that would come up in a lot of cases. So I'll just say store with a random number of customers, but you can make up your own story for it. But just to have something concrete, that's what I'm thinking of right now. Random number of customers, which is pretty realistic, right? You don't know how many customers you're going to have, and then each customer chooses to spend some amount of money, maybe zero, and then you want to know how much money you got or how much profit or whatever. So it's a very natural problem. So let's let xj be the amount that the jth customer spends. Okay, and then let's assume that there are, why did I say topics? I have no idea. Random number of customers. The number of topics in this class is fixed, which is like I say, we'll do these topics. And actually, it's not entirely fixed because I might start rambling or something and then not cover something. But actually, it's been pretty much fixed that we covered exactly what I want to cover for the most part since I've been teaching this course. Okay, so random number of customers, and let's say n equals number of customers, in a day or in a week or in some time period. So capital N, because it's a random variable, that's the number of customers. So maybe it's Poisson would be reasonable. If you had to guess a distribution, maybe you might use a Poisson, but I don't need to specify the distribution right now. I'll just say that's n, and xj is the amount jth customer spends, and let's assume xj has mean mu and variance sigma squared. So I'm assuming that they all have the same mean and variance for how much the customers spend. Of course, you can generalize this problem in different ways, but for now, let's just assume they all spend the same average. They may spend different actual amounts, but they spend the same average amount, and they have the same variance. And let's assume that n and this sequence of expenditures are independent. Okay, so we're not necessarily assuming that the x's are IID, but we are assuming that they're independent. So it's not like the second customer sees how much the first customer spent and wants to spend more than that person or something like that, or they come in in groups, in families, and decide together or something like that. They're just independent customers. And the other important assumption here is that the number of customers is independent to the individual choices for how much to spend. So, that sounds, like it may be plausible. I'm sure you can think of examples where this would break down, right? Like if n is so large that you can't fit everyone in the store, and then maybe people start leaving because it's too crowded, or maybe then they're more determined to buy a lot of stuff because then they think this is a really good, all kinds of things could happen. Or maybe n being very large is an indication that they're having some really good sale that day, and then and so on. But anyway, we're assuming they're independent. Okay, and then we want to find the mean and variance of just the total expenditures, right? That's how much revenue would you take in. So let's call that x. X is just the sum xj j equals 1 to capital N. So it's just a sum, right? Just total amount. But what's unusual about this sum is that, compared to what we've seen generally, is that the upper index here, capital N, is a random variable. So we're adding up a random number of random variables. Okay? So that's the setup. And if we just tried to use linearity, you know, your first thought may be, linearity is just a sum, then you might write, you know, E of x equals, well, there's n terms, and each one has mean mu, so you just go n times mu. However, if you did that, how should you immediately know this is wrong? Yeah. Yeah, the right-hand side is a random variable. That's a number, that's a random variable. So that would be a category error. E of x is supposed to be a number. Okay, it can be based on the various constants we have, but it can't involve random variable. Capital N is a random variable. However, so that's completely wrong. That's a category error. However, that category error actually suggests something useful to us, which is that we kind of wish that n were a constant, because if n is a constant, this is not a category error anymore. It's just saying a constant equals another constant. It might be true or false, but at least it's not a category error anymore. And if n is a constant, then really that is just linearity. So okay, so this terrible blunder actually tells us what we should do. That we wish that we knew the value of n so we could treat it like a constant. Therefore, let's just condition on n. So condition on n, that just means, well, we'll write E of x. I'll do this in two different notations. It's the same thing. We'll do E of x equals, by conditioning, so this is analogous to the law of total probability, the expected value of x given big N equals little n times the probability that big N equals little n, right? Just condition on the value of n. Now, this is the sum n equals 0 to infinity. This conditional expectation means we get to treat n that it's known to equal little n. So we know we have little n customers now. In that case, we really can just apply linearity, right? So we're going to plug in big N equals little n. And here's where this assumption is important. Because if we didn't have this assumption, what we would do is plug in big N equals little n. But just like in earlier examples we saw, like the two-envelope paradox, we can't then forget the condition, big N equals little n. In this case, though, we plug in big N equals little n. They're independent of, big N is independent of the x's, so we can forget the condition. And so then by linearity, we can just write down that is, you're adding up little n things, each with mean mu, so that's mu times n. So mu is just a constant, that comes out. And what's left in this sum, that's the sum of n times the PMF. By definition, that's the expected value of n. So we know that that's just mu times E of n. So the correction here is that this n should be the expected value of n, not n. So let's also do this using Adam's law, which is the same thing. It's just a more compact notation. So we want E of x. We want a condition on n, because then we can just apply linearity, right? It's more familiar to deal with a fixed number of terms rather than a random number of terms. So Adam's law, or iterated expectation, just says we can do E of x given n. Okay, to get E of x given n, we just take E of x given n equals little n, which was mu times little n, and we replace little n by big N. So that's mu times n. That is, we treat, this notation means treat n as a known constant, then by linearity it would just be mu n, and so again this is mu times E of n, so we get the same answer. So you can see that this is more compact than that, you know, less writing, it's shorter and nicer, but in terms of the meaning and intuition, both of these mean the same thing. So it's good to be comfortable kind of writing out longhand like this and shorthand like that are both useful. Okay, so that's the mean. Let's get the variance. So for the variance, we're going to use Eve's law. So variance of x equals, same idea, right? Condition on n. So it's the expected value of the variance of x given n plus the variance of E of x given n. Okay, now let's just evaluate these two terms. The variance of x given n. So to find that, really we just have to understand what this notation means. We're treating n as known, and then I say, what's the variance of that? Well, we know that the variance of the sum of a fixed number of independent random variables, you just add up their variances, right? We proved that before. There's no covariance terms because I assumed they're independent. So if we're treating n as a constant, the variance is just n times the variance of one term. So that's just n sigma squared plus, we need the variance of the conditional expectation, but we already found that the conditional expectation, E of x given n, is mu times n, as above. Okay, and then to simplify that a little bit, we can just take out the sigma squared. So this is E of, let's write it as sigma squared times E of n plus, and then the mu comes out squared, so it's mu squared times the variance of n. So that's the variance in terms of the mean and variance of n. Of course, I could have said n is Poisson or something like that, and Poisson lambda, and then you would just plug in lambda and lambda. But this is more general. All right, so let's quickly check whether these answers make intuitive sense. So for the mean, I think that this result is pretty intuitive because it says the average amount of money that the store will take in is the average number of customers times the average amount that each customer spends. So that's pretty intuitive. As we've seen many times, intuition can be wrong in this class, but in this case, I think this is pretty intuitive. And then for this one, let's just do a quick check that this even makes sense in terms of the units. Now, capital N or little n, we're just talking about number of people. It doesn't really have units. That's just counting people, okay? People are not units in that sense of like meters and inches and seconds are units. Now, on the other hand, mu, well, we're measuring in some dollar or euro or whatever. Let's just assume dollars. So mu is in dollars. Sigma squared is dollars squared, which is why we like to work with standard deviation rather than variance when we're trying to interpret things, because I'd rather work with dollars than dollars squared. So if we want the standard deviation, we just take the square root of that. Notice if we take the square root of this, we're going to get dollars. But if this were like mu to the fourth or sigma cubed or something, it wouldn't make any sense. You'd be trying to add dollars cubed to dollars to the fourth or something like that. It wouldn't make much sense. Okay, so it makes sense in terms of the units. Okay, so similarly, if you wanted the MGF, if you want the MGF of x, well, again, you could just condition on n. And if we knew that n is 5, then we're just adding up 5 random variables, independent. So we know the MGF, just multiply those 5 MGFs, right? So it'd be very, very straightforward. Assuming that we know the MGF of each xj, it would be very straightforward to get the MGF of this if n is a constant. Okay, but that tells us we can get the MGF in general by conditioning on n. Same idea. So you can work that one out for yourself, but it's the same idea. Okay. All right, so now we move on to inequalities. That is statistical inequalities. There are 4 of them that we need in Stat 110. So there's a sense in which inequalities deserve a lot more attention than they usually get in most courses. And so, there are different ways to explain that, but one I particularly like was I had a conversation recently with one of the leading experts in the world on the interface between statistics and the law. And he was making a point that if you're in court, as like a statistical expert witness, which is a common thing for statisticians to do, it's a lot easier if you have an inequality than if you have an approximation. So I just want to, and I've noticed a common mistake in the past in this course has been to kind of confuse approximations with inequalities. So I want to make sure that distinction is clear, then we'll go through the inequalities. The distinction is just that, like we did the Poisson approximation, right? That is, under certain conditions, you can say that a certain distribution is approximately Poisson, and that's going to be a good approximation under certain conditions. Okay, so that's extremely useful, right? Because there are a lot of problems where it's just too hard to do it exactly, but we can get a good approximation without that much effort using a Poisson approximation. For example, later in the course, we'll do normal approximation that under some conditions. A lot of conditions that are pretty realistic, that normal distributions give us good approximations to things. Those are approximations. Right now we're talking about inequalities. Now, of course, they're related. Like if I prove that a certain probability is between 0.36 and 0.38, right? So then I have both upper and lower bounds, right? And then I can say, well, the probability is somewhere between 0.36 and 0.38. So I would guess 0.37, but at least I have bounds in both directions. But if all I say is that the probability is less than 0.38, well, it could be 0.004 is less than 0.38. So that's not an approximation. That's just a bound. Okay. So that's the distinction. And the reason that this guy who I was talking to was saying that you're much happier in court if you have an inequality is that basically you can kind of imagine what would happen. Let's say I'm the expert witness and I use my Poisson approximation on something, and then you can just imagine kind of being cross-examined, right? A lot like, Dr. Blitzstein, you claimed that this approximation was good. Can you explain what you mean by a good approximation? And then I say, well, good means that it's close to the truth. And then the lawyer could say, well, is there an accepted standard about how close is? And do you know how close it is? Right? And I'd have to say, well, if I knew exactly how close it is, then I'd actually know the answer, right? And there is not a standard for what is good means. So what one person says is a good approximation, another person could say is a lousy approximation, right? It's you don't want to get into that, right? And lawyers are good at kind of tripping you up in that way. However, if I had an inequality, then I can just say the probability I've proven is less than 0.37. And then, there's basically not much that can be said about that, right? Like, I actually proved a theorem that says the probability is less than 0.37, okay? It's kind of interesting, right? Because there's still randomness and uncertainty. That's why we're using probability. But we've proven a definite fact about something random. So it's very advantageous a lot of times to have inequalities. All right, so we're going to talk about the four most important inequalities, arguably, in statistics. The first one we've already seen in some forms. That's Cauchy-Schwarz. So for random variable, a lot of you have seen Cauchy-Schwarz, in a linear algebra or math class. For random variables, Cauchy-Schwarz says that the expected value of x times y is less than or equal to the square root of e of x squared, e of y squared. That's true. You can put absolute values around it also if you want. Still true. So I was talking when we were talking about that geometric interpretation of conditional expectation. I mentioned the fact that this e of xy is playing the role of the dot product. That is, you're familiar with the dot product of vectors, and this is kind of the analog of a dot product. And so for those of you who are familiar with Cauchy-Schwarz, just in general linear algebra, this looks the same once you interpret it that way. But even if you've never seen Cauchy-Schwarz before, you can just think about what this inequality says and understand this just as its own inequality. Notice that if x and y are uncorrelated, then by definition of uncorrelated, then E of xy equals E of x, E of y. That's just the definition of what it means to be uncorrelated. So in that case, it would be crazy to use this inequality because we have an exact equality, right? And it's a better, this is just an inequality. You can see that the direction makes sense, right? Because E of x squared is bigger than or equal to E of x squared the other way. So it's true, but there will be no point, just this equals this, okay? So where this is useful is the case where they're correlated. I mean, it's good that it's true anyway, just that we don't have to break things down into separate cases, correlated case, uncorrelated case. It is always true, okay? But to see why, why this is telling us something interesting in the correlated case, kind of the cool thing about this is if we wanted to compute E of xy, in general, we'd have to use the 2D lotus, right? That is x and y, there's some joint distribution, and we would, well, either we'd have to find, we could do a Jacobian and find the distribution of x times y in the continuous case, and then, so find the PDF of this, or we could use a 2D lotus, and that could be very, very messy and difficult. So this is based on the joint distribution. This is separating it out into this is a marginal thing and this is a marginal thing. That is, this is the marginal second moment of x. That is, this is just the expected value of x squared. There's no y in this expectation and there's no x in this one, so it separates them out. So that's nice. Okay, and in the interpretation, the statistical interpretation is easiest to see in the case where they have zero mean. And this is the case we've talked about before, because if x and y have mean 0, then the correlation between x and y, well, in general, to get the correlation, we take the covariance divided by the product of standard deviations. So the covariance is E of xy minus E of x, E of y, but I'm assuming mean 0. So this is the covariance. And I divide by the product of standard deviations, but the variance of x is just E of x squared because it has mean 0. So we just do E of x squared, E of y squared, square root. That would be the correlation. And when we first, let's take the absolute value of the correlation. Well, when we introduced correlation, we proved that it's always between -1 and 1, right? So we already showed that correlation is between -1 and 1. But notice that this statement is exactly the same as the statement of Cauchy-Schwarz. Okay? So it's the same thing. So in statistics, Cauchy-Schwarz means that correlation is between -1 and 1. So I'm not going to go through a different proof of this because we already proved this fact. And this is just a small extension that says this is still true even if they don't have mean 0, and that's just a fact from linear algebra this is a very nice interpretation for our purposes. Okay, so that's Cauchy-Schwarz, and you can see why it would be kind of nice that this thing, is this joint thing, and this thing may be much easier. This is an upper bound. It may not be a good approximation, right? It's probably a pretty bad if you try to use it as an approximation. It's an upper bound, and that the strengths are simplicity and generality, not that it gives you an approximation. Okay, so our second famous inequality is Jensen's inequality, which we've already kind of seen versions of, but we haven't stated it in general or talked about it as its own topic. So Jensen's inequality says that if lowercase g is a convex function, and I'll remind you what that is, then for any random variable x, expected value of g of x is greater than or equal to g of the expected value of x. So it's pretty nice. It tells you, when you have convexity, it tells you which way the inequality is going to go, right? One of the biggest blunders in probabilities to kind of just like move the E here, move the E everywhere. You can't do things like that. And this tells you specifically which way it goes for convex functions. Okay, just to make sure everyone knows what convex function means. If the second derivative exists, it means that just the second derivative is greater than or equal to 0. That's usually the easiest way to determine if a function is convex. Just take the second derivative. So a simple example would be y equals x squared. You can draw this U-shaped thing. Y equals x squared, then the derivative is 2, which is positive, so this is convex. So at least when I took AP Calculus, this was not called convex, it was called concave up, which is kind of a stupid terminology. At least no one actually uses that, once you get past AP Calculus. This is convex. And we also had a mnemonic for how do you remember? So concave is the opposite. If the second derivative is negative, then, or less than or equal to 0, then we say it's concave. But we don't really need to study that separately, because if we have a concave function, let's just say if h is concave, all right, it just means the inequality flips. And you can see that right away, because if it's concave, just take the negative of it, and that's going to flip the second derivative from being less than or equal to 0 being greater than or equal to 0. Apply Jensen's inequality, but because of a minus sign, the inequality flips. So it just says it goes the other way for a concave. Well, anyway, we used to have a mnemonic for this, which was that concave up holds water. And have any of you heard that mnemonic before? It would be nice if it died out. So I guess I shouldn't be repeating it. Anyway, that's a very bad mnemonic, because first of all, I don't really see why concave up holds water is more memorable than concave down holds water. So it doesn't actually tell you which way it goes. And secondly, it's wrong. So like it was worth having this mnemonic just so that some mathematician could write a paper called "Does concave up holds water hold water?" And the answer was no, and he gave some examples where that doesn't actually work. So the way I remember it is just remember that this is convex. You just have to remember one simple example of a function that's convex, okay, and then go back to this picture. And this one is an especially good example to think about, because we already knew that e of x squared is greater than or equal to e of x squared the other way. We already knew that fact, because variance is non-negative. So if you ever forget which direction this inequality goes, just think back to your friendly old parabola. X squared is convex. The inequality goes this way. We already knew that, okay? So you shouldn't get confused about which way the inequality goes. So that's an example. We're going to prove that this inequality is true, just doing a couple examples first. So I should say, what's the definition? This is usually the easiest way to figure out whether a function is convex, but the definition of convex is a little bit more general. For example, if we had an absolute value function, it looks like a V shape, and that's y equals absolute value x. So the derivative does not exist at 0 because it has a sharp corner. That's still a convex function, though. So the definition is that if you take any two points on the curve and connect them, let's say like I just picked 2 points and connected them, this line segment is above the curve. That's what it means geometrically. Pick any 2 points you want, you go like that, and then it's above the curve. It doesn't cross below the curve. That's what it means geometrically. So that's true for the absolute value as well. So that's the geometric interpretation, but if the second derivative exists, it's usually easiest to just take the second derivative and see if that's non-negative. Okay, so to do a couple other quick examples, then we'll prove this theorem. What if we had the expected value of 1 over x, and let's let x be positive. Positive random variable for this part. I don't have to worry about dividing by 0 or negative numbers and stuff like that. that's x to the negative 1. So the first derivative is minus x to the minus 2, and the second derivative is 2 over x cubed. If x is positive, then 2 over x cubed is positive. So this is convex. As long as x is positive, it's convex, and this is greater than or equal to 1 over e of x. And so let's let x be positive for a couple examples. Okay, so that's true. And then what about expected value of log x? Again, I'm assuming x is positive, so I don't have to worry about the log of a negative number. The derivative of log x is 1 over x, and then the second derivative is minus 1 over x squared is negative. So it's concave, so we know this is going to be less than or equal to log of e of x. Okay, and so on. So it's pretty straightforward. Okay, let's prove that this is true now. And we should also discuss when does equality hold here. That is, in this case, we know that this only equals this only in the case when x is a constant, right? Because it says the variance is 0, which means you have a constant. Okay, so let's talk about that. All right, so proof of Jensen. So let's draw a little picture again. All right. Well, I could think of a more creative convex function, but I'm just going to draw our familiar one again. That's what a convex function looks like. Now, kind of a geometric fact about convex functions is that, which you can see in the picture, you would prove this formally in an analysis course, but just to see it geometrically, just imagine we have this convex function, and take any point, let's say here, and draw a tangent line. That was a pretty bad tangent line. But anyway, it looked too thick. This is supposed to be tangent here, and then it's below the curve, right? Or try over here, take a point here, draw a tangent line, and go like that. And the point is that draw it at 0 where it takes its minimum, then you would just have the x-axis. In any of these tangent lines you draw, it's going to stay below the curve, right? So that's the only fact essentially that we need for Jensen's inequality for the proof. That if you draw this line, so let's actually draw this line. Say this is the point mu g of mu. Okay, so that's a point on the curve, and suppose we draw a tangent line there. So that is it goes through there. Then what we're asserting is that g of x is greater than or equal to, let's say, a plus bx, or that's the equation of the line. So suppose that this line is the line y equals a plus bx. And the statement that this curve stays above the line is just the statement that the curve is above the line. Okay. Well, once you've studied the geometry enough to write down this inequality, then Jensen's inequality follows very easily, because this is true for every number, little x, in the domain that we're looking at. So that's also true as an inequality for random variables. That is, no matter what value x takes, like here we're talking about comparing random variables, I'm saying that this event, that this random variable is bigger than or equal to this one, always occurs. So we know for sure that this is true. For capital X, then just put the expectation on both sides. And then we know that e of a plus bx is a plus b e of x. I'm letting mu equal e of x. That's the notation. So that's a plus b mu. But we chose this line such that the line intersects the curve at that point. So at that point where x equals mu, this is the x-axis here, at that point x equals mu, that's the same thing as g of mu, which by definition is g of e of x. So that's Jensen's inequality. Okay, so it's a pretty short proof once you have the geometric picture in mind. You can also prove this by doing a Taylor expansion argument, but and you can look in the books for that. But I kind of like having a more geometric perspective on it for various reasons. Okay, so that just leaves two more inequalities. There are a lot of other inequalities in statistics, but this is what I consider the top four, and these are the only ones we need for this course. And you'll see why later in the semester. You'll see why we need these ones, aside from the fact that they're interesting in their own right. So the third one is called Markov's inequality. The very last topic in Stat 110 is going to be Markov chains. Same Markov, different idea. Markov's inequality says that the probability that any random variable x, let's say absolute value x, is greater than or equal to a is less than or equal to expected value of absolute value of x divided by a for any constant a greater than 0. So we're going to prove this in a minute, that the strength of this inequality is not that it gives a good an approximation, it's simplicity and generality. That this is completely general for any random variable. Of course, you have a random variable where this is infinity, and that's a pretty bad inequality, a probability less than or equal to infinity, okay, but it's still true. So in some cases, the right-hand side is bigger than 1, in which case this is true, but tells us absolutely nothing, okay? So this is a simple, crude inequality, and so let's prove it. Well, the proof is basically to use the fundamental bridge, that I'm going to convert this probability of an event. It's the same as the expected value of the indicator of that event, right? So that's the same thing as the expected value of the indicator of x greater than or equal to a. That is, I'm just using this as notation for 1 if this event occurs, 0 otherwise. That's the same thing as this, right? Fundamental bridge. And let's multiply by a. I'm just thinking of the same inequality, but with an a on the left. So I'm rewriting the left-hand side, except put the a over there. And then let's see how does this thing compare with the absolute value of x. Okay, this inequality is always true. Let's just think why. I shouldn't have do this without expectation first, then we'll bring in the expectation. Okay, so I say that this inequality is always true because there are only two cases to consider, right? Anytime you have an indicator, a random variable, either it's 0 or it's 1, right? If it's 0, that just says 0 less than or equal absolute value of x. So of course that's true, all right? That's one case. Other case is the indicator is 1. So this I sub whatever is 1. So the left-hand side just becomes a. Now in that case, if this equaling 1 says that absolute value of x is greater than or equal to a, but that's what I just said, right? Replace this by 1. It says absolute value of x greater than or equal to a. That's what we just said. So this is always true. So I'll just write, note that this is true. These are random variables, but this relationship always holds between those random variables. Once you recognize that this is less than or equal to this, then Markov's inequality just follows just by putting e on both sides. So the expected value of this indicator, take out the a, which is a constant, is less than or equal to e of x. And by the fundamental bridge, that's the same thing as Markov's inequality. So that proves Markov's inequality. Okay, so if you want a little bit of intuition on Markov's inequality, Let's think of a simple example. So then we'll do the last inequality. All right, so here's a simple little example to think about. Suppose that we have 100 people. Okay, and let's just think intuitively about a couple simple questions. I mean, we just proved this, but that doesn't make it intuitively obvious to most people. So we should think also about the intuition. Okay, suppose we had 100 people, and suppose we ask, is it possible that, let's say, 95% of the people, I'll even say at least 95% of the people are let's say, younger than the average person in the group. Average meaning mean. Is that possible? Yes. Why? You have 100 people. They all have different ages. Usually I do income here, but I'm trying to avoid that. Yeah? Older. One person's much older. So if one of these 100 people is like really, really, really old, that one person is going to pull up the average a lot, right? And so then it's easily possible that 95 people could be younger than the average, right? Because one person could pull up the average a lot, okay? So that's pretty intuitive that this is possible. If we talk about median, that's a different thing, but here I just mean mean. Okay, so that's possible. So the answer is yes. Now let me ask a similar question. Is it possible, same question, that at least 50% of the people are older than twice the average age? Take the average age, double it. Can more than half the people be older than that? No. Why not? Yeah. So it's because just taking those 50% who are more than double the average age, if you just compute their average, or the total. Let's think about the total, because if the average is mu for 100 people, then the total is 100 mu. Now suppose you had 50 people who are all bigger than double the average. Those people alone have already made the average bigger than what it is, which is impossible, right? Just those people already pulled up the average from what it was, which doesn't make sense. Okay, so that's impossible. Similarly, you can't have more than 1/3 of the people, you can't have more than 1/3 be more than triple the average age, and so on, right? It's impossible. That is exactly what Markov's inequality says. So that's the intuition. All right, so our last inequality is Chebyshev, which is another famous inequality. Chebyshev's inequality follows almost immediately from Markov's inequality, which is kind of ironic because in real life, Chebyshev was Markov's advisor. But the inequality, and both of them are famous mathematicians for other reasons, but kind of these inequalities, are very useful, but very simple. That's a crude general upper bound. Chebyshev just is basically says that, well, let me write down the inequality. It says that the probability that x minus its mean, we're just letting mu equal e of x, is greater than something. So here we're just looking at differences from the mean. Greater than some number a is less than or equal to the variance of x divided by a squared. So mu is the mean, and a is just, again, any positive number. Okay, so it's kind of similar in spirit, except we're looking at the difference from the mean, and we get variance and squared thing up here. Okay, and the other way to write this is that x minus mu greater than, let's say, c times the standard deviation is less than or equal to 1 over c squared, where, again, c is greater than 0. So this says that the probability that x minus its mean is more, that the probability that x is more than 2 standard deviations away from its mean is at most one quarter, right? 0.225. 0.25. So you can see why this is kind of crude. Like in the normal case, we had, the 68, 95, 99.7% rule, remember, which part of it says that the probability that a normal random variable is more than 2 standard deviations away from its mean is about 0.05. And Chebyshev's inequality says, well, that would always be true except with 0.25, that's 1 over 2 squared, rather than 0.05. So it's a crude upper bound. And the proof is very easy once we have Markov's inequality. No, this is equivalent to this just by letting A equals C times the standard deviation. Then those are the same thing. So to prove this first line here, let's just use Markov's inequality and just do one step first, which is to square both sides, right? So let's square both sides. And since we're dealing with, this is a non-negative random variable, this is a positive number, it's an equivalent event if we just square both sides. So that's squared. We can drop the absolute value because we squared it, greater than a squared. Now let's use Markov's inequality on this term. So by Markov's inequality, this is less than or equal to the expected value of this divided by this, which is e of x minus mu squared divided by a squared. So that's just Markov. We can put greater than or equal here. It's still true either way, but I'll write it with greater than or equal. Markov's inequality says it's less than or equal to this, right? Just immediately applying Markov's inequality there. But the numerator, that's just the definition of variance, right? So that's the variance of x divided by a squared, which is what we wanted. Okay, so that proves Chebyshev's inequality, and that's all for today. So see you next time.